Welcome back to the Lesson BCE YouTube channel. Today, we're going to see semiconductor devices, the PN junction, depletion region, barrier potential, forward bias, reverse bias, IV characteristics, construction and working of a diode, and applications of diodes. So don't forget to subscribe and like our channel. Let's get right into it.
Okay, let's lay out our clear objectives for this explainer. We're going to take you from the invisible atomic level all the way up to real-world circuit applications. By the end of our time together, you'll be able to confidently explain how a PN junction is formed, describe the depletion region, distinguish between forward and reverse bias, interpret an IV characteristic curve, and know exactly how these components are used in our daily lives. Here is our agenda for today. First, the PN junction basics. Second, depletion region and barrier. Third, forward and reverse bias. Fourth, the IV characteristic curve. Fifth, solved and practiced problems. And finally, real-world diode applications.
Section 1. The PN junction basics. Let's look at the absolute core of a diode.
So a semiconductor diode is formed by joining a p-type and an n-type semiconductor. To make doping feel a bit more intuitive, just think of the p-type side as having a bunch of empty parking spaces. We call those holes, and they act as positive charge carriers. On the flip side, the n-type material has extra cars, right? Those are our electrons acting as negative charge carriers. Now, when you bring these two materials together in a continuous silicon crystal, the exact boundary where they meet, that right there becomes the absolute foundation of modern electronics. Section 2. Depletion region and barrier. We're talking about the internal barrier.
You know, this brilliantly illustrates the PN junction, showing exactly how electrons and holes meet at the boundary. If you think about the center of that interaction, you can basically see how the energy levels and carriers clash right at that threshold. It's like a microscopic tug-of-war.
Let's break down step by step what's actually happening at that boundary. First up, electrons diffuse from the n side over to the p side. Second, holes move from the p side to the n side. As they cross paths, these charge carriers basically cancel each other out. They recombine near the junction. And finally, as they recombine, they leave behind fixed ions. This creates a sort of no man's land with almost no free charge carriers, which is appropriately named the depletion region. And essentially, it acts just like an insulator.
Now, those fixed ions in the depletion region don't just sit there doing nothing. They produce an electric field that actively opposes any further movement of charge carriers. We call this the barrier potential. The absolutely crucial threshold to remember for your exams is this. You need about 0.7 volts to push through a silicon barrier and 0.3 volts for a germanium barrier. Just think of it like a tiny built-in battery that's constantly pushing back against the current. Section 3, forward and reverse bias. This is all about controlling the current.
Okay, so in forward bias, we hook up the positive terminal to the p side and the negative to the n side. What happens? Well, the depletion region thins out, and once we overcome that 0.7 volt barrier, current just flows super easily. But in reverse bias, we flip the whole shebang. The positive terminal goes to the n side, and the negative goes to the p side. This actually causes the barrier to widen, basically turning the diode into a one-way valve for electricity that effectively blocks the current. You're left with almost zero flow, just a tiny microscopic leakage.
Moving on to Section 4, the IV characteristic curve. Let's map out voltage and current.
Check out how this behaves on a graph. During forward bias, the current is basically zero until it hits that magic 0.7 volt threshold for silicon. After passing that knee voltage, boom, the current shoots up rapidly like someone just flipped a closed switch. On the flip side, representing reverse bias, the current is virtually zero until it gets pushed way too far and hits the breakdown voltage. At that point, a massive and potentially damaging current flows through.
Mathematically, this one-way behavior is represented by this equation right here, where I is the diode current, IS is the reverse saturation current, V is the applied voltage, and VT is the thermal voltage. But look, from a practical standpoint, just remember this main outcome. Below about 0.7 volts for silicon, you get almost zero current. Above 0.7 volts, that current increases exponentially. It really is that simple.
Section 5, solved and practice problems. It's time to test your knowledge. Let's look at a quick solved example. We have a silicon diode connected in forward bias with 0.8 volts applied. So, will it conduct? Well, since our applied 0.8 volts is clearly greater than silicon's known 0.7 volt barrier potential, we know for absolute certain that the diode will allow current to flow. It's successfully overcome that internal resistance. Easy, right?
Now I actually want you to pause for a second and think about this practice problem.
A germanium diode has a barrier potential of 0.3 volts. Your applied forward voltage is 0.25 volts. Will it conduct significantly? Have your answer? Okay, no, it definitely won't conduct. And why? Because 0.25 volts is less than the 0.3 volt barrier. The depletion region hasn't been overcome quite yet.
Section 6. Real-world diode applications. Let's see some actual real-world uses for this stuff.
Diodes are literally everywhere, and mastering these tiny little components is incredibly important for modern technology. From safely blocking reverse battery connections, which is known as reverse polarity protection, to smoothing out AC power into DC using rectifiers, diodes really are the silent heroes of our electronic devices. I mean, they even give us light through LEDs and keep our power supplies perfectly stable using special Zener diodes. They're total game changers.
So, to wrap everything up, here are the essential takeaways you absolutely need to remember. A diode is essentially a one-way street formed by joining P and N-type semiconductors. That depletion region acts as an insulating barrier. Forward bias allows current to flow easily, while reverse bias actively blocks it.
Before we go, I want to leave you with this exciting thought. If a simple two-layer PN junction acts as a one-way valve, how might stacking 3 layers together completely revolutionize modern computing? Well, that right there is the foundation of the transistor, and it's definitely a topic for another time. Thank you so much for watching. Keep learning physics with Lesson BCE, and please don't forget to subscribe, like, and share this lesson.